Hey, Edgar B. Herwick III here, and this is our inaugural edition of Soft Serve with Scientists. The idea here is, can a big brain scientist tell me all about their work and have me understand it in the time it takes us to eat a soft serve? Who do we have with us today? What's your name? What do you do here?
I'm Pablo Jarillo-Herrero, and I'm a physicist.
You're a physicist. What kind of physics do you do?
I do quantum materials.
What does that mean?
It means that I study materials with interesting quantum properties.
Okay, and what's your specialty in these quantum materials space? What is the thing that you do that nobody else really does?
The thing that I do is called twistronics.
So is it like this? I mean, this is a twisted ice cream. How is it like this and not like this?
It's like this, but a million times thinner.
A million times thinner.
A million times thinner.
So very, very thin.
Yeah.
So what is twistronics all about?
It means we can change the properties of material, the electronic properties of materials, by changing the twist angle, the angle between materials.
The angle between materials. So
yes.
you twist materials together.
Yeah, we twist them all the time.
Okay, so what's special about it aside from the fact that they're very, very small? Very thin, at least you say.
What happens is that we can take a material which has a certain property, for example, it's a conductor, but just a conductor. It conducts electricity, and by placing another two-dimensional material on top. It's important, this is done with two-dimensional materials, ultra-thin materials.
Two-dimensional materials.
One atom thick.
One atom thick.
One atom thick.
That's it. So we have two one-atom thick materials. We stack them on top of each other, and then you just twist them together?
Yeah. And then we can make each, the combined two materials behave like any material in the universe.
Wait a minute, what do you mean, any material in the universe?
Well, I take a conductor.
Okay.
It's just a conductor.
Just a conductor. What's a regular conductor?
The one I use is called graphene, but for example, copper.
Copper.
But we don't do this with copper because copper is three-dimensional. It has to be two-dimensional.
Two-dimensional.
Like two cards, of a deck of cards. Okay. So we take two cards.
Yep.
And rather than placing them exactly on top of each other, like it happens when you make a deck of cards, we just twist them on top of each other.
You just twist them on top. How do you actually twist them? How do you do this?
Well, we take a long card, we cut it in two pieces, we take one and put it twisted on top of the other.
Okay. Had nobody thought to do this before? You're the first person to do this?
Some people have thought about it, but I found the magic angle.
What's the magic angle?
It's the angle that if you twist one on top of each other at that angle, 1.1 degrees.
1.1 degrees?
That's right, very precise. Then magic happens.
And what kind of magic can we do? I mean, it sounds, to hear you say we can make it behave like any material in the universe sounds incredibly useful and impressive, but I don't know if that's true or not. Is that true? And what are the kinds of things you can now do with this material that you can make behave like any material in the universe?
For example, we can take a conductor which is known as graphene, put it on top of itself twisted, and then we can make it behave like an insulator, so now it doesn't conduct electricity, or like a superconductor, it conducts electricity without dissipating energy, or like a magnet, like a kitchen magnet, or like any other property of any material in the universe.
That's crazy.
It is crazy.
What is it about the magic angle? Like, how does it work? Like, why does that happen?
Well, I brought a little toy here to show you. So, when we put, graphene on top of graphene, it's these little hexagons that you see here, okay?
Yep.
And we put graphene on graphene. If we now twist it, you can see, I'm going to do this, you can see that it forms a Moiré pattern, a special pattern.
Oh, neat.
And now, each of these big balls behaves like a superatom. And I can do chemistry with those superatoms, without doing chemistry actually, it's all electronic. Yeah.
So, who wants this stuff and who's going to use this stuff? And what are they going to use it in?
Potentially, it could be useful for many things. Since we can do it all with just carbon, with just one material, right? We don't need rare earths, we don't need any other material.
So can we just stop using, I mean, in the future, can we stop using everything we're using to make all of the stuff that we make and just use this?
Not quite.
Not quite.
Yeah.
So not quite that.
Yeah. Partly because we don't know how to make these two-dimensional materials twistronics at scale.
I see.
Yeah. Right now, it's still basic science research. Physicists like me, we do it one device at a time. We need to make millions and millions of devices, all identical, working. But it's very hard because this is like, imagine you take kitchen plastic wrap,
and
you take two sheets of plastic wrap, you put them one on top of each other, twisted, but there cannot be a single wrinkle whatsoever.
Yeah.
Not even a one atom thick wrinkle.
So
Right?
how
So
do you
that's
pull that
fine.
off? Control conditions.
Ourselves, we do it. We know how to do it for one device.
What one device?
I mean, with one device at a time. You know.
I see.
I can put 2 graphene sheets,
I see.
twisted at a magic angle. You know, I can do it once. It takes me 2 weeks, 3 weeks.
It takes that long?
Yeah.
Because you're just being that careful
to make
twisting
magic, it takes a lot of
It's magic here. Come on. I got it. So the idea is like to have a factory or something that can do this at scale
we
is
need to
like
make
you're way
billions
off
of
from
them.
that.
Yeah,
I got it.
that's
I
right.
got it. So
But
what
yeah,
are,
it's the beginning, so
okay. What's the first stuff you like? Let's imagine you get to some level of scale.
yeah.
What's the first couple of things that, like who would be most excited about this coming online and saying like, oh, once you guys figure out how to make this stuff, I want it.
There are many things that one can do. One can do, for example, the most sensitive detectors of light. Okay? And not visible light, but light that we cannot see with the eye, which is they're much harder to make detectors, good detectors for that.
For like ultraviolet and infrared
No,
light?
for infrared, for low energy light.
I see.
Infrared or
Okay.
terahertz or
So people who
microwaves.
make telescopes would want this.
Yeah, astronomers would love to have those. Yes.
Okay. Who else?
We can also make devices now that consume much less energy than the devices we use now for AI. So there are these devices called neuromorphic devices, neuro as in neurons,
Neuromorphic.
neuromorphic.
So they
idea
morph
is
your brain.
That's right. The idea is we want to compute like our brain does, which is thousands of times more energy efficient than
Yeah.
our data centers are.
Yep.
So we can make neuromorphic devices which have never been done before with this 2-dimensional twistronics. And if we manage to do them at scale, potentially we could use a lot less energy in our data centers.
Interesting.
Yeah.
Interesting. And producing a lot less heat, a lot less like impact, all of that stuff.
That's right.
How did you even begin to start being the person who's figuring this out and solving this problem? How did you come to this?
Well, in the history of material science,
Yeah.
we have never been able to change the angle between planes. Nature doesn't allow you to do that. But if you have 2-dimensional materials, like a card out of a deck of cards,
Yeah.
now I can just take one and put it on top of another one.
Yeah.
We weren't able to do that before, but now we can do it.
Does it, I mean, it sort of feels a little bit like alchemy, you know what I mean?
It totally is, except that it's the opposite. There's this thing, medieval alchemists, they try to find this thing called the philosopher's stone,
Yeah.
that everything that you touch, you turn it into gold.
Yeah.
This is the same, except the other way around.
How so?
Because we have one material, carbon, for example, graphene, and with that, we can make everything else. Rather than turning everything into gold, is we turn one thing, carbon, into everything else. So it's an inverse philosopher's stone, and because it's a quantum material, it's a quantum inverse philosopher's stone.
How long have you been working on this?
15 years now.
15 years. So
Yeah.
in that time period, over those 15 years, were there moments where you were just like, I'm going to give up because this is not possible?
Well, the truth is that we didn't know we were going to find this inverse philosopher's stone.
Oh, really?
No.
What did you
We-
think you were going to find?
No, we were just curious. We've never been able to change the angle between materials. Whenever you explore or look at something where you've never been able to do it, interesting things are going to happen. So we were sort of like explorers in the jungle trying to find something interesting. We had a sense that something interesting might happen, but
Yeah.
what we found was 10 times more interesting than we thought.
Who was the first person you told when you like worked this out and you were like, I did it, we can do it? Who did you tell?
We did it, my graduate students and I. So we were all sharing there, and we had this moment where we nearly started crying. We couldn't believe that this would happen. Yeah.
Really?
Yeah.
Do your friends and family understand what it is you do, or like when you tell them what you do?
A little bit, yeah.
Yeah.
My family, they're not scientists, but I tell them, what graphene is, it's a one atom thick material.
Yeah.
This analogy with the deck of cards and the cards. So,
yeah. They kind of get
They
it.
kinda get
I
it.
feel like I kind of get it. What's the next thing for you now that you've sort of worked this out? What are you going to be working on looking forward?
Well, we can do 2 cards on top of each other, or we can do 3 or 4 or 5, and the properties change all
Yeah.
the time.
Yeah.
So We also have many types of cards. Mostly we've been using a card made of carbon atoms called graphene. But we can do this with many other materials that we have 1 atom thick cards. So we can do this with all kinds of materials to realize even more exotic behaviors. And the cool thing is to discover a new, it's called phase of matter, a new behavior that didn't exist at all before. That's like the coolest thing.
Why do you think that's so cool?
Because you find out something that is completely unknown, that no one had ever imagined, ever worked with, ever done. And that to me is very exciting.
Is that what keeps you coming to work every day, is just like chasing that feeling?
Yeah.
Yeah. All right. Cheers.
Cheers.
There you go. Twist, what's it called?
Twistronics for twist electronics.
Twistronics. I get it.
All right, so we need to do another one.
Really? Are you serious? Because it was too messy?
No, it was great.